Bismillahirrahmanirrahim. In today's class, we are going to talk about beam elements. And up until now, we have talked about springs, bars, 2D trusses, and 3D trusses. And today we are going to see that what forces and moments are there in case of beam elements. So with that, we will be considering this element whose length is L, and the forces at nodes 1 and 2 are F1y, F2y, and the displacements are V1 and V2. The moments at node 1 and node 2 are M1 and M2, and the rotations at node 1 and 2 are phi1 and phi. Global x-axis or the local x-axis, they both match with each other. Here is the x-axis and here is the y-axis. The displacement along y-axis is denoted by v. All right, so here we have shown the sign convention. So moments are positive in the counterclockwise direction. Similarly, rotations are positive in the counterclockwise direction. Forces are positive in the y direction, and displacements are positive in the y direction. This is the sign convention that we are going to follow for the nodal forces and rotations. All right, so now we'll basically try to derive the element stiffness matrix for a beam element, and we'll start from scratch. So let's consider a beam element which is subjected to an arbitrary loading whose magnitude is omega x. This is x-axis, this is y-axis, displacement along y-axis is denoted by v. So we will consider a small element of this beam, and the shear force on this face is v and the moment is m, and after small distance dx, the shear is v plus dv and the moment is m plus dm, and the load which is acting on this element, small piece of element, is omega x. So we write down the equation of equilibrium for this differential element, and for that purpose, let's say first we write down sigma m right side equal to 0. So basically this point is our moment center. Okay, so if we consider, let's say, this moment first, so m plus dm, it is in counterclockwise direction, so we take it positive, and then this m is in clockwise direction, so minus m, and minus v into dx. This is v and dx is the lever arm. This is our moment center, and it is producing moment in the clockwise direction, so we take it as negative. And then the moment produced by the resultant of this area load. Omega x into dx is the magnitude of the resultant, and it will be acting at the center. So dx by 2 would be the lever arm. And in the last term, we see that dx we'll have the square of dx, which is approximately equal to 0 because dx by itself is a very small distance. So this will get cancelled. Similarly, this m and m minus m will get cancelled. So in the next slide, you'll see we'll use the simplified form of this equation by cancelling these terms. And similarly, we can apply sigma fy equal to 0. And for this, v is acting in the upward direction, so positive v, and this v plus dv is acting in the downward direction, so with a negative sign, and this area load is also acting in the downward direction, so minus omega x into dx, and that is equal to 0. And if we look at this equation, this v and minus v, they will get cancelled, and we can simplify this equation. All right, so from force and moment equilibrium of a differential beam element we get, so these are the expressions that we get after simplifying the equations that we have seen here. After cancelling out the terms and neglecting this term, we get the uh, we get this version of the equation, or we get v equal to dm over dx, and that's something that we already know from our undergraduate knowledge, that shear is equal to the derivative of the moment equation. So v is dm over dx, and similarly from sigma fy equal to 0 we get this equation. If we simplify it, we get w equal to dv over dx with a negative sign. And if in this expression we plug in the expression for v, which we have obtained here, so we get w equal to d by dx of dm over dx. Or in other words, we can write down that w is equal to double derivative of moment with respect to x. And we also know the curvature relationship. The curvature of a beam is the moment curvature relationship. Again, we know it from our undergraduate knowledge that K is equal to 1 over rho, and that is equal to M over EI. This K represents curvature and rho represents the radius of curvature. And we know that both are inversely proportional to each other. If we have a beam, as the curvature of the beam increases, its radius of curvature decreases. So this is the old moment curvature relationship. All right. So where rho is the radius of deflected curve or elastic curve, v hat is the transverse displacement and function displacement function in the y direction. E is the modulus of elasticity, and I is the principal moment of inertia about y. This is basically a typo. This is actually about z direction as shown in the figure below. So we have this center line of the beam. Uh, Omega x is the load acting. Displacement in the transverse direction is Vx. And here the radius of curvature is shown. It is equal to rho, and the curvature for small slopes is equal to dv over dx. So we know that if we know the displacement and we take its derivative with respect to x, we get the slope. And if we take its derivative one more time, we get the curvature. So curvature is d2v by dx2. And we also know that this Okay. We also know the moment curvature relationship. So finally, we get M is equal to EI d2v over dx2. And this equation is also known as the equation of elastic curve, right? If you remember that in mechanics of materials at the undergraduate level, we use this equation to calculate the deflection of the beam as well, right? If you remember the double integration method, then in double integration method we use this relationship, and this is our basic relationship. That's we call it the equation of elastic curve. We take its integral, and that gives us the slope, and then we integrate it one more time, and we get the displacement. So that's the same old equation. All right, so now if we substitute, we go back to this slide. M is equal to EI d2v by dx2. And if you substituting the moment expression into the moment load equation, we get this form of the equation. Basically, here we are using uh, this relationship. W is equal to double derivative of M with respect to X. And we have plugged in the expression for M, and we have got this expression. So for constant values of EI, the above equation reduces to this form. So if we take the fourth derivative of the displacement, we get the load. Okay, so that's the relationship between the load and the displacement. Now let's perform those steps which we have been performing to derive the element stiffness matrix. And the first step would be the selection of element. So the element type, as we discussed at the very beginning, this is the type of element that we'll be considering with the nomenclature, that there are two forces, F1y and F2y at the nodes, and two moments, M1 and M2 at the nodes. Corresponding rotations are phi1 and phi2, and the corresponding displacements at node 1 and 2 are d1y and d2y. Now, uh, we will assume the transverse displacement relationship of this form, and we have discussed that many times earlier, that polynomial type of functions are the most popular type of function to be used as displacement function. And in this case, the nodal degree of freedom of each node is 2. So the degree of freedom of the entire element is 4. So we can consider uh, a polynomial function with 4 coefficients: a1, a2, a3, and a4. The number of coefficients in the displacement function ai is equal to the total number of degrees of freedom associated with the element, displacement and rotation at each end. So the boundary conditions are, now we know that at displacement at node number 1 is d1y. So we can say that at x is equal to 0, we have, at x is equal to 0, v would be equal to d1y. And at x is equal to L, v, at x is equal to L, v1, v1 will be equal to, or v would be equal to d2y. And similarly for rotation, at x is equal to 0, rotation is phi 1, and at x is equal to L, rotation is phi 2. And if this is v, we can take its derivative with respect to x, and that derivative will be used uh, in order to substitute these boundary conditions. So dv by dx, if you take its derivative, it would be 3a1x square plus 2a2x plus a3, and this a4 will become equal to 0. So these boundary conditions will be plugged in the expression for v and dv over dx. And when we apply these boundary conditions, for example, the first one, v at 0 would be equal to d1, v at x is equal to 0, that's equal to d1y. And when we plug it in this expression, we get d1y equal to a4. And similarly, we can use all the 4 boundary conditions, and we can get the values for, or expressions for, a1, a2, a3, and a4. And these expressions will be used in the expression for v. There are some intermediate steps which have not been performed here, uh, just to because those things are basic. So when we do those intermediate steps, when we plug in these values of a1, a2, a3, and a4 in this expression, then the form that we get is here. So v turns out to be this expression, and this expression can be rearranged in a way that we have the we separate the coefficients of all the degrees of freedom. That what is the coefficient of d1y, d2y, phi 1, and phi 2. And when we do this, then we can make one vector for the displacements or for the degrees of freedom, and the other vector will give, or other metrics will give us the shape functions. So displacement vector would include d1y, phi 1, d2y, and phi 2, and shape functions would be, the vector of shape functions would be n1, n2, n3, and n4, and these will be the expressions for n1, n2, n3, and n4. These are expressions can be simply obtained by just rearranging this equation such that we separate the coefficients for d1y, phi 1, d2y, and phi 2. There are no other mathematical steps involved. All right, and this is the graphical form of these shape functions n1, n2, n3, and n4 for the beam element. All right, next is define the strain, displacement, and stress strain relationships. So, okay, here is a typo. There are a few typos in these slides. I will just keep on letting you know. So this is the basically the strain displacement relationship, not stress displacement relationship. So the strain displacement relationship, we know that epsilon is equal to du by dx, where u is the axial displacement function. We can relate the axial displacement to the transverse displacement by considering the beam element shown below. Okay, let's see how we are going to make use of that. So if this is the part of the beam, part of the deformed beam, then what is this slope dv by dx? This slope. So if we have, if let's say we draw a tangent at this point, what will be the slope of that tangent? The slope of the tangent would be dv by dx. And similarly, we know that uh, the uh, the section would be perpendicular to that tangent. Okay, and it's if the slope of the tangent with respect to x-axis is dv by dx, then the slope of this section with respect to y-axis would be dv by dx. And then we consider this set of triangles here, and this is the neutral axis. The distance between the neutral axis and this extreme fiber would be minus y, and this angle is dv by dx. So this theta is approximately equal to dv by dx, and displacement u would be equal to minus y times dv by dx. If we consider this triangle, let's say this is the base of the triangle and this is the angle dv by dx, then this perpendicular would be equal to u would be equal to minus y into dv by dx. So one of the basic assumptions in simple beam theory is that the plane section remains plane after the deformation. So the strain epsilon xy is equal to O minus y d2v by dx2, because we know that strain is the derivative of the displacement. So we take its derivative, we differentiate it one more time with respect to x, and we get the strain. Moments and shears are related to the transverse displacement as this. We know that if we have transverse displacement and we take its double derivative, we multiply that with EI, we get the moment. And if we take the third derivative of the displacement and we multiply that with EI, we get the shear. Okay, now the step number 4, derive the element stiffness matrix and equations. So using the beam theory sign convention for shear force and bending moment, we obtain the following equations. So this F1, F2, M1 and M2, these are the nodal forces and moments, and these are the shear force and moment as per the beam theory. So we know that if we take the third derivative of the displacement and we multiply that with EI, we get shear. We have the expression for V with us, so we take its third derivative, we multiply that with EI, we get this expression. And similarly, if we use that third derivative in this expression for the other end, we get this expression, right? Just with a with the opposite sign, because the sign convention for the nodal forces and the sign conventions for the beam theory, they are opposite to each other. And we know that moment, if we have the displacement, transverse displacement, we take its second derivative, we multiply that with EI, we get the moment. So we take the second derivative, multiply that with EI, and we get this expression. And similarly, we can get the expression for M2. Now, if we just simply rearrange these equations in terms of the nodal degrees of freedom, then we can express these equations in the matrix form like this. So F1y M1 F2y M2 is equal to EI over L cube. This matrix into D1 y phi 1 D2 y phi 2. This basically this matrix, this this is the matrix form of this equation, of these equations. Okay, so if we express these equations in the matrix form, we get this relationship. And in this relationship, we have the forces or the degrees of freedom, forces and moments on this side, and we have the degrees of freedom on this side. And this matrix is the stiffness matrix. So this matrix, and we call it K. So K is equal to EI over L cube. And this matrix, this is the element stiffness matrix for a beam element. Okay, now this was the case when the local and global axis, they were coinciding with each other. But we know that just the way this, in case of trusses, we have elements for which the local axis and global axis, they do not coincide with each other. Similarly, for beams, we have such cases when the local and global axis do not coincide with each other. So we have to derive the element stiffness matrix for the element in the arbitrary orientation, right? So we can derive the stiffness matrix for an arbitrarily oriented beam element in a manner similar to that used for the bar element. So here is the element which is making an angle theta with respect to x-axis. So the local axes are x prime and y prime, and the global axes are x and y. The displacements in the local uh, y direction, they are y1 prime, y2 prime, and the rotations are phi1 prime and phi2 prime. Length of the element is L. So the local axes are, this crosses, and local axes are located along the beam element and transverse to the beam element respectively, and the global axis, this is x and y, not x prime and y prime, are located to be convenient for the total structure. All right, now the transformation that we studied previously when we were talking about the bar element, the transformation of the displacement, those relationships are actually true in general. Those relationships were not specific to the bar element, right? Rather, those were general relationships. So, similarly, in this case, if we have to transform the displacement, we can make use of those relationships. And in the bar elements, we had only axial displacement, so we make use of the first relationship, which is for u, that u prime is equal to cv plus sv. And in this case, we have transverse displacement, so we'll make use of the relationship of v prime. So v prime is equal to minus su plus cv, where c is cos of theta and s is sine of theta. So using the second equation for the beam element, we can relate local nodal degree of freedom to the global degree of freedom, right? So this relationship that we are using is basically from this relation. So V1, and we know that in case of beam element, the degrees of freedom are V1, phi1, V1 prime, phi1 prime, V2 prime, and phi2 prime. And those have to be related with the global degree of freedom, U1, V1, phi1, U2, V2, and phi2. Now, an important point to note here is that if you look at this rotation is about which axis? This rotation is about out of plane axis. So whether this element is along the global x-axis, like along this x-axis here, or it has some angle with respect to the global x-axis, as it has in this case, this rotation phi1, it's basically about out of the plane axis. So the out of plane axis remains the same whether we are considering the local coordinate system or the global coordinate system, which means that no transformation is required for phi. So whether it is phi 1 prime or it is just phi 1, basically both of them are same because both of them are about out of plane axis, and whatever is the orientation of the element in the plane, the out of plane axis remains unchanged. So you see that if you use this relationship here, phi 1 prime is basically equal to phi 1. There all other entries are 0. Only you will have the expression for v1 prime equal to minus su1 plus c1 and so on. Right. Similarly, if you look at the expression for v2 prime, it would be minus su2 plus cv2, right? And phi 2 prime will also be equal to phi 2. So phi is basically they remain the same. So here we can see that say that d prime is equal to this transformation matrix into d. So this is the transformation matrix. Notice that the rotations are not affected by the orientation of the beam, as I have explained earlier. All right. So another relationship which we saw earlier, and that is valid for the other cases as well, that this when we do the transformation, then the transformed stiffness matrix is equal to the transpose of the transformation matrix into the element stiffness matrix in terms of the local coordinates into the transformation matrix, right? So this relationship we looked at its derivation earlier for the bar element, and that's also true for the beam element. So when we do all of this multiplication and manipulation, then we get this matrix, and the degrees of freedom are u1 v1 phi 1 u2 v2 and phi 2. Similarly, you can label the rows. So this is a 6 by 6 matrix, and this matrix is the element stiffness matrix of a beam element in terms of the global coordinate system. Okay, the element stiffness matrix which we derived earlier for the beam element, that was the element stiffness matrix for a beam element when the local axis and the global axis they coincide with each other. However, this element stiffness matrix is in terms of the global coordinate system, or in other words, for the arbitrarily oriented beam element. Okay. The next concept that we are going to discuss is that how we can consider the effect of an axial force, because we know that if we are just considering an isolated beam, uh, in that case there will be only shear force and bending moment. However, if a beam is a part of a frame structure, then it will have axial forces as well, right? So you can say that this is a beam element with an axial force, or you can also call it a frame element because it will have axial force, shear force, as well as bending moment. So the difference between this case and uh, the element beam element that we have just considered is of this axial force. If you look at the previous figure, there was no axial force in that, but here we have axial forces. So this is x prime axis, and the force along x direction is F1 x prime, F2 x prime at node number 2, and the corresponding displacements are U1 prime and U2 prime. Now, here for this frame element, uh, we will basically, we are not going to make the derivation again. Actually, we have already seen that how to deal with the axial forces acting on the bars as well as the transverse forces and the bending moments. So now we are just going to combine those pieces of information. Okay, so if you recall that simple axial deformation defined in the spring element or the bar element was this one: f1 x prime f2 x prime is equal to ae over l, 1 minus 1 minus 1 1, and u1 prime and u2 prime. So this is nothing new. This is from the bar element or from the spring element. And here what we have done, we have actually, as I said earlier, we have just compiled that information, that whatever degrees of freedoms are involved, whatever forces and movements are involved, we have just compiled them in one matrix, right? So for spring or for bar element, we have f1 x prime, f2 x prime only. For beams, we have f1 y prime, m1 prime, f2 y prime, and m2 prime. And in case of an arbitrarily oriented beam having an axial force, we have all of these forces and moments. So we have combined basically this matrix, this information, and the matrix for the beam element, and we have got this 6 by 6 matrix. So you see that, before combining them, what we need to do, we need to make sure their coefficients are consistent. For example, here we have outside of the bracket we have AE over L, whereas in this case, wait a minute. Yeah, in this case, we have EI over L cube. So we cannot just combine these two matrices directly. So what we have done here, we have taken these coefficients inside of the bracket so that we can combine these matrices together. So we have taken those coefficients inside, and then we have called C1 equal to AE over L, C2 is EI over L cube, and those have been taken inside the matrix and they have been compiled here. So if we have a beam element with the axial force, then it has these 6 degrees of freedom: U1 prime, V1 prime, phi 1, U2 prime, V2 prime, and phi 2 prime. And this is again for the case when the beam is along, means the local axis and the global axis, they coincide with each other. However, if they don't coincide, then what we have to do, then we have to do the transformation. So let's see how that can be done. So this is the above stiffness matrix includes the effect of axial force in the x prime direction, shear force in the y prime direction, and bending moment about the z prime axis. Okay. So this is the element stiffness matrix, and the local degrees of freedom may be related to the global degrees of freedom by this relationship. And again, here we have just compiled that information. So if you look at that, let's say you look at the first row, and u1 prime comes out to be c u1 plus s v1. That's our old relationship. Similarly, v1 prime comes out to be minus s u1 plus c v1. That's again old relationship. And phi 1 prime will come out to be phi 1. Similarly, with these, the next three elements of the matrix can be seen, right? So basically, we have just arranged uh, the information which we already have about the relationship between the local and the global degrees of freedom. So this is our where T has been expanded to include the axial effect. So this is our transformation matrix. D prime is equal to T times D, and substituting the above transformation T into the general form of the stiffness matrix. And, and how do we obtain this? We obtain this by multiplying transpose of T with the stiffness element stiffness matrix like this one in terms of the local coordinate system, and multiplying that with T, the transformation matrix. So when we calculate T transpose K prime into T, then we get this matrix. This is a much more complicated matrix. It is a 6 by 6 matrix, and this is the matrix for the stiffness matrix for beam element which is arbitrarily oriented and has axial force, shear force, as well as bending moment. So this is probably the most comprehensive type of element that we have studied till this point. So it's a beam element with arbitrary orientation and having uh, axial force, shear force, as well as bending moment. Okay. So the next concept that we are going to discuss is related to the inclined or skew supports, just the way we did it for trusses. And the concept is actually very similar. So let's see how to deal with skew or inclined supports. So if a support is inclined or skewed at some angle alpha for the global x-axis as shown below, the boundary conditions on the displacements are not in the global xy direction, but in the x prime and y prime direction. So the boundary conditions for this case would be along x prime and y prime direction, which are at angle alpha. Now let's see how to deal with them. So we must transform the local boundary condition v3 prime equal to 0 in local coordinates into the global xy system. So the actual boundary condition is in terms of the local coordinate system, and we need to transform it to the global coordinate system so that we can apply the boundary condition to the global stiffness matrix. All right. So the relationship between the components of displacement in the local and the global coordinate system at node 3 is, so at node 3 we have, if I go back to this diagram, we will have the displacement in the y prime direction. Displacement would be restricted, and displacement along the x prime direction would be allowed. And the transformation of the displacement in local to global coordinate system basically is governed by the same relationships. u3 prime is equal to cos of alpha into u3 sine of alpha into v3, and that's it. Similarly, v3 prime is equal to u3 minus u3 sine of alpha plus v3 cos of alpha, and u3 phi 3 prime is equal to phi 3. That we have already discussed that rotation is about out of plane axis, so there is no transformation required. And this thing can be written in the brief form as d3 prime equal to t3 d3. This t3, this matrix is t3. Now, why we are talking about this, um, like the third node only? The reason is that the skew support is at node number 3. If we have skew support at node number 3, then we will consider the u2 prime, v2 prime, and phi 3 prime, and so on. So this is our transformation matrix for node number 3, t3, and we can apply this sort of transformation to the entire displacement vector. So d prime would be equal to di into d, or if we just multiply both sides with the inverse or with the transpose of ti, we get d equal to ti transpose d prime, where this ti transpose is equal to this matrix. Now, how we construct how we have constructed this matrix. Uh, these identity matrix and this T3 matrix, yeah, these are 3 by 3 matrices, and as we do not have any skew or inclined support at node number 1 and node number 2, so we do not require any transformation at these nodes. That's why we just put identity matrices here and here. At node number 3 we have a skew support, so we need transformation. So we put T3 matrix at node number 3, and we have already seen that the composition of T3 matrix will be like this. And I repeat that, yeah, we are doing this for node number 3 only because we have a skew support here. Let's say in your case, the problem that you are solving, you have a skew support at node number 2, then you will make T2 instead of T3, you'll make T2, and that will be placed here, and at this place you will have identity matrix. So that's how we make transformation matrix in order to deal with the skew support. So the force vector can also be transformed by using the same transformation. So f prime would be equal to ti into f. So we multiply the force vector with the transformation matrix, and we get transformed force vector. In global coordinate, the force displacement equations are F is equal to KD. That's a simple basic relationship. So applying the skew support transformation to both sides of the force displacement equations. So we are multiplying, we have considered this relationship, we are multiplying it with Ti on both the sides. So TIF is equal to TIKD. And by using the relationship between the local and the global displacements, the force displacement equations become So this side TIF, it remains the same, and on the right side we have this TI, the K is the same. This D can be replaced with Ti transpose into D prime, which we have seen in the last slide. D is equal to Ti transpose into D prime. So Ti transpose into D prime, and we know that this Ti into F is what? It is F prime. So F prime is equal to Ti K Ti transpose D prime. Actually, we uh, we derived exactly a similar relationship for the trusses having skew supports. And this relationship in the expanded form, we can write down this force matrix and displacement matrix, we can expand them. So here is the force vector and here is the displacement vector. And you see that in the force and displacement vector, we have this prime only with the entries related to the third node, because these transformation matrices that we have considered here, they have the composition uh, uh, in such a way that only the degrees of freedom at node number 3 are being transformed, right? So we have these primes with the forces, movements, and degrees of freedom at node number 3. However, in your case, if the skew support is at node number 1 or at node number 2, then the situation will change accordingly. Okay, so that's the concept of dealing with the skew support in case of frames.